Everyone, thank you for joining. My name is Ahmed Balawi. I'm from the Innovation Department. And today I'm going to give you a brief overview about the ACWA Power hydrogen R&D. So what do we do in R&D in terms of hydrogen? So I prepared some slides to give you a brief introduction about the market also of hydrogen, but Idris just covered it, so I'm just going to go through it quite fast. So obviously, clean hydrogen is an energy vector. We can think of it as a liquefied natural gas or the diesel of the future. It can be done by basically taking advantage of regions that are rich in resources in order to transform energy into hydrogen and then transport it to areas with less availability. So this map here shows different colors, the turquoise colors representing Saudi Arabia, which is rich in abundant and complementary renewable sources like solar and hydrogen and wind, which can then be transformed into hydrogen and transported to other regions with less availability. Also, the map on the right side shows the distribution of clean hydrogen projects around the world in terms of production and also in utilization. It's clear as of January 2023, the amount of projects that are being invested in clean hydrogen is around $320 billion. And it's important to note that in order to reach our 2050 net zero goals, the investments in such projects needs to be at least doubled by 2030. So when we talk about producing hydrogen, there's really a spectrum of methods into producing hydrogen, and with that spectrum comes obviously the spectrum of hydrogen colors, going from high carbon into low carbon. Black carbon for producing hydrogen through coal, and then gray hydrogen producing through steam methane reforming. And if we capture the CO2, then it's labeled blue hydrogen. And then comes the more cleaner hydrogen, like turquoise hydrogen through methane pyrolysis, and water electrolysis through renewables produces green hydrogen. So at ACWA Power, our R&D activities is mainly focused on clean hydrogen, and more specifically the green and turquoise hydrogen. So to start with green hydrogen, this is a study by McKinsey and the Hydrogen Council that shows the projection of the cost of blue and green hydrogen along the years. And they're projecting that the cost of hydrogen, producing hydrogen in regions that are optimum with the renewable resources can go down to $1.5 per kilogram, such as in Saudi Arabia. So now it's important to ask this question, how can we reach down to these prices, low prices? Especially by 2050. In order to do this, it's important to look into the levelized cost of hydrogen. And this is let's say, a simple formula of the LCOEH. And in order to drop down the cost, we can lower down the investment cost. We can produce more hydrogen in terms of efficiency and also lowering down the operational cost or the price of electricity. So it's really important to also look into the efficiency of the electrolysis because it can produce more hydrogen at a lower cost or lower consumption of electricity. So in order to look into the technologies of producing hydrogen, then there are four leading, let's say most leading technologies into hydrogen production, and they can be categorized into low temperature or high temperature electrolysis. With the most mature technology being the alkaline electrolyzers, and the rest of the technologies are still at a low technology readiness levels. For example, there's the anion exchange membrane or the AEM, which is very similar to the alkaline, but uses a membrane to transport the hydroxide from the cathode to the anode. It reduces the probability of crossover of hydrogen through the electrodes and also has a faster variable load operation. Then there is the PEM, the proton exchange membrane, that uses a membrane to transport the protons from the anode to the cathode. And this is an efficient process. It can operate at a larger operational window and also fast response with high purity of hydrogen. And lastly is the high temperature solid oxide electrolysis cells, or SOEC, which is the most efficient electrolysis technology. And also it can be coupled with downstream processes like methanol, ammonia production, or e-fuels. So in order to direct the research, it's important to understand the advantages and disadvantages of all these technologies, and they're here, let's say, summarized in this table. We're looking in terms of R&D beyond the alkaline, because alkaline is also designed for operational or fixed operational conditions. So other technologies we're looking into is the AEM, anion exchange membranes, which is lowest in cost. However, it's still produced in a small scale, small area stacks, and also they are, let's say, they don't have long-term operational conditions. They have a faster degradation rates. Then PEM, which is the highly efficient electrolysis. However, it is quite high in terms of capex because it uses really rare materials like iridium, ruthenium, or even platinum. Finally, the SOEC, which is the highest efficiency in terms of energy consumption. However, it's still in a small scale system size, and it lacks there are some questions regarding the durability and also the high capex cost. So now transitioning into the projects that we're working on in the green hydrogen. The first project is a collaboration with KAUST, specifically with Professor Shulu. He's going to delve into more details into this project. And in this project, we are benchmarking the performance of PEM and AM electrolyzers, and also coupled with PV system and battery system in a microgrid scenario. So the objective of the study is really to understand the difference between the PEM and AM in terms of efficiency of production, about the stack degradation rates, the hydrogen purity, and also all of these parameters, how do they change instantaneously with the change of PV loads. And with this project, we also developed a control algorithms to optimize the LCEH, specifically when it was coupled with intermittent PV loads. And we started with a certain algorithm, and then by running more experiments and collecting more data, we will work step by step into optimizing this algorithm, the control algorithm, in order to optimize the LCEH. Another project that we're working on, we're also developing our in-house comprehensive tool in order to simulate the performance of electrolyzers. The motivation around this work is basically the lack of commercial tool that can act or can give us the objective or the simulation capabilities. And with this simulation tools, we're also looking into electrochemical models, we're looking into thermodynamics models in order to take into account the different technical aspects of different electrolyzer technologies and also the economics aspect of it. So that simulation tool is developed for design purposes, for project development purposes. However, we're also going beyond this, and we're also working on developing a performance model for really an operation and maintenance purposes. So by collecting data from the pilot plants, utilizing it to develop these performance models, we can get insights into the operation of the plant, and towards, let's say, operation maintenance of replacement of stacks, potential degradation, or any safety hazards. So with this, I conclude with the green hydrogen projects, and I'm going to move into the turquoise hydrogen. So what is turquoise hydrogen? It's basically a methane pyrolysis process. Methane pyrolysis is the breaking down of a methane molecule into solid carbon and hydrogen, where the solid carbon can be collected and sold to different markets, for example, the carbon nanotubes market. The motivation behind going through this methane pyrolysis is basically that the energy required or the enthalpy for breaking down a methane molecule is around 7 times lower than the energy required to breaking down the water molecule. So this project is in collaboration also with KAUST, with Professor Mani Sarati, who will give the talk after me and go through this project in more details, where they developed the process flow diagram and optimizing what kind of feed conditions for the natural gas and also the processes. And by doing the study, we also published techno-economic assessment papers, and we moved towards the next phase of building a pilot plant in the lab in order to study the effects of temperature on the methane pyrolysis using a 12 kilowatt thermal electrical heating lamp. And with this, I would like to conclude. I hope I give you a brief about this R&D activities and also our collaboration at KAUST. And I'm looking forward to expand further into this ecosystem and potentially having more collaboration projects. Thank you.